In this video, I want to take a look at how we calculate transition matrices so that we can then convert coordinates with respect to one basis to coordinates with respect to another basis. Okay. So as a reminder from the last video, here's the basic problem. We're in a vector space V and we've got two bases. Basis B being U1 up to UN and basis B prime being W1 up to WN. Notice, of course, they have the same number of elements because all bases of the same matrix, or sorry, all bases of the same vector space must have the same numbers. So anyway, we're going to be given one other vector, V, which we know the coordinates with respect to the first basis, basis B. So the coordinate vector of V with respect to B is A1, A2 up to AN. Find the coordinate vector with respect to basis B prime, which we're going to call B1 up to Bn. Okay. Now, if we happen to know that all of the UIs can be written as, well, we know that they can be written as the W's, but if we know what they are, so we know that UI is K sub I1, W1 plus K sub I2, W2, plus all the way up to K sub IN, WN. Then I know that I can convert to the B's by multiplying my coordinates with respect to the first basis times this matrix, right? This is what we had at the end of the last video, where we said the transition matrix was supposed to be, the columns were the vectors of the original basis written in terms of the new basis. Okay, so that would be what this matrix is right here. The question is, how do we find that matrix? Because the problem is we're trying to convert to matrix B prime, and so I've got to do all of the U's to B prime before I can convert the vector V to B prime. Just doesn't seem like the smart way to go. So here's an actual example. Okay, I'm going to work through how we do it on a small example. So I've got basis B here. I'm in R2, so I've got just two vectors in my basis, and the vectors are going to be the vector 3, 2 and the vector 1, 1. Okay. I ask you to consider the following. This matrix here, where the first column is the matrix 3, 2, and the second column is the vector 1, 1. So I'm making a matrix out of these vectors, but writing them as columns. Okay. In all of what we do here, it's kind of funny because we talk about B and B prime as my bases, but there's another set of bases lurking in the background because there's the standard basis. If we're in R2, we know there's a basis ij, right? 1, 0, and 0, 1. And in fact, the way we write our vectors is component vectors with respect to that basis, right? To say 3, 2 means it's 3 times 1, 0 plus 2 times 0, 1. That is, this is already the way that I would write this vector with respect to the basis, the standard basis, okay? And this is what I would call the standard basis S here, 1, 0, 0, 1. Right? So my columns of that matrix are the vectors of my original basis written in terms of the standard basis. So according to the theorem we had right at the end of the last video, this matrix should be converting coordinates from basis B to the standard, right? And notice, if you write U1 with respect to basis B, well, U1 is one of the members of basis B, so that would be 1 times U1 plus 0 times U2. So with respect to basis B, the coordinates of U1 is 1, 0. And if I take 1, 0 and I multiply it by this matrix, I get 3, 2, which is the coordinates of U1 with respect to the standard basis. So multiplying by this matrix converted this vector from basis B coordinates to basis S coordinates. Okay. Likewise, if we did it with U2, where U2 would be 0, 1 when you're talking about coordinates with respect to basis B, because it's 0 times U1 plus 1 times U2. But if I multiply this matrix times 0, 1, I get second column here, 1, 1, which is the coordinates of U2 with respect to the standard basis. So multiplying by this matrix is converting base B to standard, base B coordinates to standard coordinates. And I claim that this process is invertible in that I could say, well, I want standard coordinates converted to basis B coordinates. And, well, wouldn't that be just the same as multiplying both sides of this by the inverse of this matrix? And this matrix happens to be invertible. I can see the determinant is 3 minus 2, the determinant is 1. In fact, I can even write down what the inverse of that matrix is. The inverse of that matrix is this. With a determinant equal 1 and a 2 by 2 matrix is pretty easy. Just swap the two things on the main diagonal and change the signs on the off diagonal, and then divide by the determinant, which is 1. So this matrix here is the inverse of that one. So my claim is that this will convert coordinates basis S to basis B. Okay, so let's try it. Here's the vector 1, 3, 2. That's standard basis. That's our U1, right, with respect to the standard basis. If I multiply it by this matrix, I get 3 minus 2, which is 1, and I get minus 6 plus 6, which is 0, which is 1, 0, which happens to be U1 written with respect to basis B. So this was with respect to basis S. This was with respect to basis B. It converted S to B. Likewise, if I multiply by 1, 1, which was my second basis vector, times this matrix, I get 1 minus 1, 0, and negative 2 plus 3, 1. So this becomes 0, 1, which is U2 written in terms of basis B. This was U2 in terms of S. This is U2 in terms of B. So indeed, it does convert basis S to basis B coordinates. The original matrix was B to S. The inverse is S to B. What this does now is it gives me a way of converting from basis B to basis B prime by taking a stop at basis S in the middle, right? Go from B to S and S to B prime, and I can very easily write down what those matrices are, right? So here's my theorem. If T is an n by n matrix whose columns are the components of basis vectors from a basis B with respect to the standard basis for Rn, then T is the transition matrix from B to standard. That's what we've already said. Furthermore, T is invertible, and the transition matrix can go the other way from standard to basis. Okay, that was that one. So let's move on to the next. Here's the way to transition now, and here is my theorem for that. If B and B prime are two bases for Rn, and I'm going to denote matrices here, the matrix B and the matrix B prime are the matrices obtained by making column vectors from the elements of each of the bases with respect to the standard basis. So that's exactly what we did up here, that this matrix right here was the matrix B, right? Not the basis B, but the matrix that's made from the basis vectors, right? Each vector is a column, right? So do that for both B and B prime. Then the transition matrix that converts coordinates with respect to B into coordinates with respect to B prime is take B prime inverse and multiply by B, right? And then to do the conversion, you take your vector on this side with coordinates with respect to basis B, you multiply it by this matrix, which converts it to S, and then you multiply by this matrix, which converts it to B prime. Okay, and each of these is reasonably easy to write down anyway. So here we go. I'm going to do basis B is U1, U2, where I got 2, -1 and 5, -3 are my two basis vectors, and then B prime is the 3, 2, 1, 1. This happens to be what we call B up above, but I'm using it as B prime now. So the matrix B is just take these two as columns. So 2 minus 1 is the first column, 5, -3 is the second column. Basis B prime turns into the matrix B prime 3, 2 is the first column, 1, 1 is the second column. So I'm claiming that my transition matrix from B to B prime is this inverse, so B prime inverse B, so this inverse that, this inverse I calculated up above was this, and you multiply them together, and you get this matrix, 3, 8, negative 7, negative 19. Let's see if that works. So I'm just going to pick a random vector here. Actually, what I did is I took my basis B, and I said, let me grab two numbers here, 3 and negative 2, take that linear combination. So this vector here, negative 4, 3, is 3 times u1 minus 2 times u2. So the coordinate vector for negative 4, 3 with respect to basis B are these two coefficients here written as a list, 3, negative 2. Right? Now, if I take 3, negative 2, and I multiply it by this matrix that I just calculated up here, I get, what would this be? 9 minus 16, which is negative 7, and minus 21 plus 38, which is 17. This was supposed to be the coordinates of negative 4, 3 with respect to B prime. So let's check. If I take negative 7 times the first thing in B prime, plus 17 times the second thing in B prime, do I get negative 4, 3? I think I do, because this is, what's that, minus 21 plus 17? There's negative 4. And this is minus 14 plus 17, which is 3. So yes, indeed, negative 4, 3 is negative 7 times the first vector in B prime plus 17 times the second vector in B prime. And so the coordinates of negative 4, 3 with respect to B prime are indeed negative 7, 17, which we got by this multiplication. Okay. Now, so the way I think of these transition matrices is I think of them in terms of converting to standard basis and then converting out of standard basis to the one you want. Because it's really easy to convert from any basis coordinates to standard. You just make a matrix that's got your basis vectors as the columns written in terms of the standard basis, which is the way we would normally write them anyway, right? And then in order to get out of standard to the basis you want, you write the same matrix here, but this converts from B prime to S. So in order to turn it around, you take the inverse. And remember, you're starting with your vector on this side, on the right. So then you first multiply by B to get to standard, and then you multiply by B prime inverse to get to the B prime basis. Okay. The way the book says to do this calculation is not wrong. It's just, well, let's describe it. They say to make a bigger matrix here. So take all the columns of B prime, all the vectors of B prime, make them columns, and then next to that put all of them in B. And then go to reduced row echelon form. Now this is very much like what we did for calculating inverses, right? If I want to do the inverse of B prime, I would do this, but I have an identity matrix over here on the right. And when I put this in a reduced row echelon form, I get an identity matrix on the left, and it would have been B inverse over here on the right. Well, it turns out what's actually happening is that the process of reducing this to row echelon form is essentially multiplying this whole matrix by B inverse. And so the left-hand side turns into the identity, and the right-hand side turns into B inverse times whatever was there. Well, if whatever was there was B, then this transition matrix is, as I said up here, B prime inverse times B. Okay. Now, so in order to calculate the transition matrix, this is a perfectly good way of doing it. However, it's a process for finding the transition matrix, but the result in itself is not the transition matrix. It's just the right-hand side of it that's the transition matrix. Where writing it this way, you actually have the transition matrix. It's B prime inverse times B. That converts coordinates with respect to base B into coordinates with respect to base B prime. There's a bunch of these in the homework for you to try. You can do your calculations either by the book's method or by my method. They both are equally good. So have fun.